Okay, now part D asks, the ball is now 10 meters below the man, so he's now a 10-meter distance below the guy. And we were asked to find the velocity of the ball when it's down here. Okay? Now, it turns out this problem is almost exactly identical to part C. Okay? Now, the only difference is that our final height is 10 meters below our initial height. Okay? So therefore, y final minus y initial is no longer 0. It's minus 10 meters. Okay? So if this is our let's say this is a height of, 20 here. Okay? And this was our initial height, that's a height of 30. 20 minus 30 is minus 10. So that's the key difference in this problem from part C. Everything else is exactly the same. We want to know what the final velocity is down here. So this still holds. We want to know what the final velocity is. This equation still best fits this set of variables right here. Now, the big difference is when we don't get 0 here, okay? 2 times the y acceleration, negative 9.8, times delta y, which is minus 10. Okay? So we go through the same set of steps here. You do this multiplication. You multiply this out, add these two terms together, take the square root, and the answer you get is you get a plus and minus answer, but again, we want to keep the negative one. That's the one that makes sense. That's the downward motion. We get 20.5 meters per second. Okay? Now we're now asked in part E if there's any difference at all if we instead throw the ball straight downward at minus 15 meters per second. So here's the situation now. Okay, the guy throws the ball straight downward at minus 15. Minus because it's downward. Okay, remember we have to make sure we have the sign straight. So minus 15 meters per second. Okay, so the difference then up here is that this is actually minus 15 meters per second. Everything else is the same. In part D, we had delta y is minus 10. It's still minus 10. We're still interested in the velocity 10 meters below the cliff. So this stays at minus 10. We still want to know what the final velocity is. So we use the same equation because we have the same set of variables we're interested in. Now, the only difference is that our y initial was minus 15. Okay? But when we square this, we get the same answer as if we just had 15 squared. So when we do that term out, we get the exact same answer we had in part D. Okay? Because minus 15 squared is 15 squared. So there's our result, same as in part D. So basically what's going on is we get the exact same answer whether this guy throws the ball straight up at 15 meters per second or whether he throws the ball straight down at minus 15 meters per second. Okay? Because if he throws the ball upward at 15 meters per second, when it comes back down to his hand, it's moving downward at 15 meters per second. It's exactly the same as throwing the ball straight downward at 15 meters per second. Okay, now we know that's not the case in our everyday lives. In our everyday lives, if you threw the ball straight up, it's not going to return back to your hand at the same speed because there's air resistance. So you throw something straight up in the air, when it comes back to your hand, it's actually traveling slower than when it left your hand because of air resistance slowing it down. So in real life, if you throw something straight down at 15 meters per second, it's going to be traveling faster than if you threw it straight up at 15 meters per second. But in this idealized situation with no air resistance, you get the exact same answer.